Welcome back, everyone. So today we'll be going over systems of linear equations again, but this time we'll be approaching the applications of them. So systems of linear equations are incredibly versatile and find relevance in a wide variety of applications. In this section, we'll explore two fascinating applications, and stay tuned because there's more to come in the next chapters. Now, let me ask you something. Have you ever wondered how to fit a polynomial function to a set of data points in a plane? Or how networks and Kirchhoff's law for electricity are connected? Well, we're about to find out. So let's consider these points in this xy plane. We have x1, y1, x2, y2, x3, y3, x4, y4, and x sub n and y sub n. We have all of these points, and our goal is to best represent them in the expression as a function. And the best way to represent that is like this. We have p of x is equal to a sub naught plus a sub 1 of x plus a sub 2 x squared plus, and it goes on to include a sub n minus 1 times x n minus 1. Now in this function, this procedure is called a polynomial curve fitting, where all the x coordinates are distinct as points, and there's precisely only one polynomial function of degree n minus 1 or less that fits the endpoints as shown in the graph. So, what if we were to solve for n? Well, to solve for the n coefficients of p of x, we would have to draft a system of linear equations, and it will look something like this. A sub naught plus a sub 1 x1 plus a sub 2 x2 squared plus, and as we've already discussed, it's all in the sequence, and of course this is equal to y1, and y2 would have to equal a sub naught plus a sub 1 x2 plus a sub 2 x2 squared plus a sub n minus 1 x squared n minus 1, and this should be 1 as well. And this is more of a general solution. In the next example, we're going to be more specific. Okay, so here's a more specific example. Let's say you're given a polynomial with these points, and with the given graph, you're supposed to determine the polynomial whose graph passes through these points. So it's basically asking, what's the solution to this graph? What's the equation? And how do you find it? And going back to the previous example, we know that p of x is equal to a naught plus a sub 1 of x plus a sub 2 x squared, and so on and so on. And we're given a few points: 1, 4, 2, 0, and 3, 12. Okay, so we're given 3 points. What does that mean exactly? Well, with these 3 points, we know what p is at 3 different x positions. Now, what do I mean by that? Well, let me make this smaller and it's still legible. So, the first point, 1, 4. What does that mean as an equation? Well, when x is equal to 1, we get p of 1 is equal to a naught plus a sub 1 times 1 plus a sub 2 1 squared. And this equation is simply a naught plus a1 plus a2. Okay, let's remember that. Now, what happens if x was 2? Well, what the pattern follows us, a naught plus a1 times 2 plus a2 times 2 squared, where p of 2 is just a naught plus 2a of 1 plus 4a of 2. Now, tell me, what happens when x is equal to 3? Well, if you said it was a naught plus 3a1 plus 9a2, you'd be correct. Now, this is perfect because we actually have a system of equations after doing some of the math presented right here to us. Okay, let me just make that 4a2, and this one can be 2a1 for neatness. Hold on, there we go. So look over here, and guess what? This isn't exactly perfect. Do you know why it's not perfect? Because p of 1, p of 2, and p of 3, they're already defined in the graph. So let's just change that real quick. So when p is equal to 1, it's 4. No, when x is equal to 1, it's 4. And when x is equal to 2, it's 0. And at x equals 3, we get 12. Alright, now do you see a pattern here? Do you see a solution to the system? Because we got everything we need. And feel free to pause the video, but if you were to apply Gaussian elimination to this problem and get into row echelon form, which you should be familiar with, we should have a solution given where a naught is equal to 24, a sub 1 is equal to negative 28, and a sub 2 is equal to 8. Therefore, given these values, what is p of x? Well, referring to the general equation from earlier, it should be 24 minus 28x, oh, that is a terrible x, plus 8x squared. Go ahead and look at this equation. Does it fit the graph? And if you do your Gaussian elimination for your system of equations, do you get the same solutions? Go ahead and give it a try, let me know. And to cut it short, this would be the right solution. And yes, it does match our graph as the polynomial passes through these 3 points. Alright, now we're on to another example with a more nuanced graph. So, in this graph, you're given a polynomial function, and you're given 5 points this time, starting with 0, 1, negative 2, 3. Man, I really need to work on my 3's. Negative 1, 5, 1, 4, and 2, 10. Okay, in this graph you have 5 points. If you are given 5 points, what degree should your polynomial function be? Please take your time to answer that. And If you don't have the answer, just go back a little bit. Okay. If your answer to that question was that it shouldn't be a fourth degree polynomial, then that's okay, because it is. So remember, p of x is equal to a naught plus a1x plus a2 x squared plus a of n minus 1 times x of n minus 1. We're given 5 points, and when n is equal to 5, the function should be a fourth degree polynomial function. So now that we got that out of the way, let's think about what that means exactly. It just means that our function is a sub naught plus a sub 1x plus a sub 2x squared plus a sub 3x cubed plus a sub 4x to the fourth. And of course it does equal some constant, and we are getting 5 points. So let's just think this through and ask ourselves, what is that supposed to look like? What's the dimension of this system of equations? Okay, so if you did some thinking, which I hope you did, this should look like a 5x5 system of linear equations. So let's start off with the point negative 2, 3. So at p of negative 2, we should have a naught plus a naught minus 2 a1 plus 4a2 minus 8a3 plus 16 a sub 4. And we know that when x is equal to negative 2, y is 3. Right on. Okay. Now what about when x is equal to negative 1? When x is equal to negative 1, p is equal to 5. And we simply plug in negative 1 to our x values within the fourth degree polynomial. So as a result, we get a naught minus a1 plus a2 minus a3 plus a4. Now let's move on to when x is 0. When x is 0, p of x equal to 1, and we just get a naught, because 0 times anything is 0, right? Okay. Now, what about when x equal to 1? What does that equation look like? When x is equal to 1, p of x is 4. And we get a naught plus a1 plus a2 plus a3 plus a4. I'm pretty sure that's right. 1 to the power of anything will always be 1. Now, what happens when x is equal to 2? Well, you get the same equation as the first one, the top one. But since it's a positive 2, it's going to look a little different. How so? We're about to find out. So when x is equal to 2, p of x is 10. And we get a naught plus 2a1 plus 4a2 plus 8a3 plus 16a4. And voila. This is our system of equations. And we already got one solution. And I'll have you guys wonder, what is it? Well, we have a sub 0, which is 1. And normally your professor would not make you do this by hand. Your calculator should have a function that produces solutions for a 5x5 systems of equations. And let's be real here, none of you guys are going to do this by hand. So, if you plug this into your calculator, we already got the first one. And a sub 1 is just negative 5/4. A sub 2 is just 101 over 24. Okay, that can't be simplified. And A3 is 3/4. And A4 is negative 17/24. There we go. We have our solutions. Now, can you do this by hand? Absolutely not. Well, let me take that back. Yes, you can do this by hand, but the real question is, do you even want to? And believe me, I am 100% sure that your professor will not make you do this by. They won't make you do this matrix especially by hand. So, we have our solutions. What does our polynomial look like for this given graph? Well, I'll have you guys figure that out, but it should look like this. 1 minus 5/4 x plus 101/24 x cubed plus 3/4 x cubed, okay, minus 17/24 x to 4th. And there you have it. So the system of linear equations in this example is relatively easy to solve because the x values are minute. For a set of points with large x values, it's best to translate the values before attempting the curve-in procedure. Now, what do I mean by that? Well, we're about to find out, don't worry. So, in this example, the prior two were relatively easy to solve because the numbers were much more manageable. However, what if you're dealing with big numbers? How are you going to find a polynomial with x values that are big? So, let's say, okay, let's say x1, y1 is equal to 2011 and 3. x2 and y2 is equal to 2012 and 5. x3, y4 is equal to 2013 and 1. Forgive me, everyone. This should be y3. And x4, y4 is equal to 2014, 4. Yeah, today is just not my day. x5th, y5th is equal to 2015 and 10. Yeah, try putting that in a system of equations, especially a fourth degree polynomial equation. So, what do we do? Or more specifically, what's the best way to approach this problem specifically? So since these x values are humongous, we're going to use the method of translation. And that involves having z is equal to x minus 2013. And, well, yeah. Why did I do this again? So, in a graph, we have x and y coordinate, but what if we were to manipulate the system equations and have it set to, instead of terms of x and y, but what if we set to terms of just one single variable? And we can do that by having x and y equals z, and even more specifically, having z equal to x minus 2013, which is the smallest x value in this table in these systems of points. So let's replace x with z and let's see what will happen. So let's say, what happens if we turn x1 into z1? Well, we have 2011 for x1. Let's plug into the z equation, and as a result, we get z1 y1 is equal to -2 and 3. Okay, that's very manageable. What if we switch x2 with z2? Yeah, that makes sense. Yeah. What if we do the same for x2? Okay. We end up having z2 and y2. Plug x2 into the equation and we get -1, 5. Okay. What about x3? Can we put that into the z equation? Most definitely. By now you guys should be able to see a pattern here. And we can do the same for x of 4. And we 1/4. Then for a 5th point, we get, I think it's 2/10. Yeah, 2/10. Wow. Do you guys see what we did here? Okay. So we've changed the x variables and have them be in terms of z. And that's great. Well, yeah. It's great because this system of equations, it looks so much more bearable now. And I have to ask, what do we do now? Well, it's the same process as the last example, now that our variables are much easier to work with. So since this is the same set of points as the prior example, we can now write a new function in terms of z, and we get 1 minus 5/4 z plus 101 over 24 z squared plus 3/4 z cubed minus 17 24 z to the 4th. Now, if you're wondering where did I get this function from, they're the exact same numbers from the prior example. I just wanted to help you guys incorporate the method translation in this one. Okay, so take a gander at this table right here. How are we going to create a polynomial that relates the periods of the 3 planets closest to the Sun to their average distance from the Sun? More so, how can we use this polynomial to calculate the period of Mars and compare it to the values shown in the table? Now, for those who are curious, the mean distance will be in astronomical units and the periods will be in years. So I'll give you guys time to think about that. Let me bring you guys back a bit. So we're given this. Damn, stylus went out again. Come on. Okay. Always remember, p of x is equal to a0 plus a1 of x plus a2 x squared. Oh, and disclaimer, you are going to see this equation a lot. So, the system of linear equations obtained by substituting certain points into p of x will be the mean distance of both Mercury and Venus. So let's plug in the mean distance to this polynomial, and as a result we should get a0 plus 0.38781 plus 0.387 squared a2, which is equal to 0.241. And as for Venus, we have a naught plus 0.723 a1 plus 0.723 squared a2, and that equals 0.615. And for Earth, we have a naught plus a1 plus a2, which is equal to 1. Okay, so we have 3 equations of the 3 closest planets closest to the sun. Good. Everything's looking promising. And what's next exactly? Well, you have everything you need pertaining to the 3 closest planets to the sun. And it's just going to require some old school Gaussian elimination. And if you were to work this out through Gaussian elimination, or let's be honest here, you probably have a fancy calculator that does the solutions for you, you should get 3 approximations. A naught is equal to negative 0.0634. A1 is approximately 0.6119. And A2 is, well, it's not equal, but it's approximately 0.4515. And then we have our 3 points. Well, what do we do next? And if you said plug into a polynomial, you are correct. So A naught is 0.0634 plus 0.6119x squared. No, it's just x. Plus 0.4515x squared. Voila. This is the approximation of the polynomial function for the 3 planets closest to the sun. Now, as I've recalled, what if we plug in, well, I'm going to do something real quick. I'm going to plug 1.524. Oh my god. Why? Why did I do that? Well, recall earlier that I asked you guys to calculate the period of Mars after deducing the polynomial. So, we had the polynomial. We can then use the average distance from Mars, which is given in the table as 1.524, plug it into the polynomial, and we should get the period. And after a 30-second approximation, that's about 1.981 years. So let's note that the period of Mars is shown in table as 1.881, which it's close. It's a really close approximation. And as we demonstrated in the prior example, a polynomial that fits some of the points in the dataset is not necessarily an accurate model for other points in the dataset. Fundamentally, the further the other points are from those used to fit the model, the worse to fit. For instance, the average distance of Jupiter from the Sun is 5.03 astronomical units. If we use the polynomial equation we have right now in example 4 to approximate the period, it will give us 15.343 years, which is a horrendous estimate of Jupiter's actual period of 11.862 years. So, yes, the concept of curve fitting can be difficult And these types of functions, other than polynomial functions, may actually provide better fits. So, what do I mean by that? Well, we're about to find out. Okay, so what we have here is the same table, but with the natural log of the average horizontal distance and the natural log of the period. Why did I do this? Well, suppose we fit a polynomial to a logarithm of distances and periods. What kind of relationship will that produce? And if you were to say that it would produce a relationship such that the natural log of y is equal to 3/2 the natural log of x, you would be correct. And if this relationship is linear, what would that look like exactly? Go ahead and plug in the natural log values into your calculator and let me know what you guys get. Okay, so this is your graph with the relationship between the natural log of x and natural log of y, and you'll see that it's a perfectly linear graph. Now our equation is natural log y is equal to 3/2 natural log of x, and it follows that y happens to be 3/2 x. Okay everyone, where did I go wrong? Turns out that if you were to exponentiate both sides, this would actually be x 3/2 is equal to y. Or if we were to square both sides, get y squared is equal to x cubed. In other words, the square of the period in years of each planet is equal to the cube of its average distance from the sun. And historically, Johannes Kepler discovered this relationship in 1619, which is the reason why you may have heard of Kepler's law. Okay, so when I mention network analysis, what comes in mind exactly? And if you were to think along the lines of economics, traffic analysis, and or electrical engineering, you would be correct. Now, in a network model, you assume that the total flow into a junction is equal to the total flow of a junction. In layman's words, you get what you put in. So, how can we represent that algebraically? Well, let's say you have a junction right here. This is your circle. And you have a line going into it, and which you put in spews out into two nodes. And let's say the line going into the dot is 25, and the output are x of 1, x of 2. So the junction shown below has 25 units flowing into it. So what does that mean exactly in this context? Remember, you get what you put in. So if you put 25 in, you should get 25 out. And algebraically, this can be represented as x of 1 plus x of 2 equals 25. Each junction in a network gives rise to a linear equation, so you can analyze the flow through a network composed of several junctions by solving a system of linear equations. The next example will elaborate on that. Okay, so in this example, we have a diagram, and I strongly advise you write this down too. And along certain lines, we get some of them are defined as x variables, some are defined as coefficients. So, based on this diagram, how many junctions do we have? And what would our linear equation even look like? So, let's look at x1 and x2. We know, oh, you know what? It'd be very helpful if I numbered the blue dots. So, top left one is 1, 2, middle one is 3, bottom left is 4, bottom right is 5. Okay. This should make things a lot easier for you guys. So, let's observe x1 and x2. x1 is going from 1, 4, 5, 1. Okay. So, we have to look at the direction of each x variable. And if you notice, x1 and x2, they tend to be going with the flow. And at some point, they end up mating or converging at 20. As a result, our system of equations will look like this. And this will be junction 1, which we denote as J sub 1. Now for our second junction, let's look at x3 and x4. So x3 is going from 2, 3, 4, 5, and fundamentally with the flow. x4, however, it is going against the flow from 5, 2, 3. Well, it's going backwards against the flow, as I said before. And therefore, the equation will be x of 3 minus x of 4, which is equal to negative 20. Now, what about x of 2 and x of 3? So, x of 2 and x of 3 are actually both going with the current or with the flow. So therefore, both the terms are positive. And as a result, we get x of 2 plus x of 3, which is equal to 20. So we have our second junction and our third junction. However, there are a couple more that we have to go over. Let's look at x1 and x5. So x1 we've already established going with the flow. x5, however, in relation to x5 and relative to the 10 defined, it's going against the 10. So in our fourth junction, x1 will still be positive, but x5 will be negative. And it will end up equaling negative 10. And there's one more junction. Can you guess what those are? So, x4 and x5 relative to 10. So, x4 is going against the flow relative to 10. And x5 in relation to 10, it is also, it's actually going with the flow. It's going with the flow. So therefore, negative x4 plus x5 equals negative 10, and we have our, these are our 5 junctions, and each of the network's 5 junctions gives rise to a linear equation as shown here. Now, the terms, they go up to x of 5, and if you were to convert that to an augmented matrix, what would that look like exactly? I'll give you guys time to write it out. Okay, so if you were to convert your your systems of linear equation to an augmented matrix, it will look something like this. Now, the only way to find a solution to this matrix is to apply Gauss-Jordan elimination, and as a result, you get a matrix that ends up looking like this. From the matrix above, what would if you were given this matrix after applying Gauss-Jordan elimination, what would the equations look like? So, we know that the last row wouldn't exist, so we would have 4 equations. And as a result, we get x1 minus x5 is equal to 10, negative 10. And then we have x2 plus x5 is equal to 30. Then we have x3 minus x5 is equal to negative 10. And x of 4 minus x of 5 is equal to 10. So these are our new systems of linear equations. And let's say, what if we let t equals x5? Because in a row of zeros, we know that x5 cannot be any real number based on the new augmented matrix. So if we substitute x5 for t, what would those equations look like? Well, I know for the first one, it'd be x1 equals t minus 10. And what would x of 2 look like? It will look something like this. It's negative t plus 30. And this one, the third one, that would be x of 3 is equal to t minus 10. And this equation, this should be x of 4 minus x of 5. And with that out of the way, we should have 10 plus t. And we know x of 5 can be t, where t is any real number. And there you have it. So because of the row of zeros, we can let x of 5 be any real number. And in addition to that row of zeros, it's very indicative that the post-Jordan elimination matrix will have infinitely many solutions. Okay, in this example, you are given a circuit. Your voltages are defined, and your resistors are defined. But how do you find currents for I1, 2, or 3? And more importantly, how do you do network analysis on this specific diagram? So an electric network is another type of network where analysis is commonly applied. Analysis of such system uses 2 properties of electrical networks, and those are known as Kirchhoff's laws. And it follows 2 rules. All current flowing into a junction must flow out of it, so therefore, mathematically, junction coming in is equal to the junction coming out. The second postulate is that the sum of the products of current and resistance, where I is current and R is resistance, around a closed path is equal to the total voltage. And we're going to remember those rules when we're applying network analysis. And according to this diagram, let's go over the components within it. So we have current, which is measured in amps. Resistance is measured in ohms, and it's denoted by the Greek letter omega. And the product of current and resistance is volts. Volts, they're represented by the two vertical lines, and those vertical lines usually represent battery. And the large vertical bar denotes where the current flows out of the terminal, and the symbol with the squiggly lines denotes resistance. The arrow within the branches show the direction of the current. So if we were to apply the first rule of Kirchhoff's law, we know, well, if you apply first rule of Kirchhoff's law to the circuit, what do you notice? Well, for one, I1 is following the path of path 1, and I3 happens to be following path 2. Where exactly do they converge? And if you say they converge at I2, you'd be correct. Therefore, mathematically, I1 plus I3 is equal to I2. Now, in the next step, you're supposed to apply Kirchhoff's second law. And how are you supposed to do that? Well, do keep in mind we have two paths. We have path 1 and we have path 2. Mathematically, we can represent them like this. R1, I1 plus R2, I2 is equal to 3I1 plus 2I2, which equals to 7 volts, and R2, I2 plus R3, I3 is equal to 2I2 plus 4I3, which equals the 8 volts in path 2. So we have, after applying Kirchhoff's first and second law, we end up having a system with 3 linear equations. And for the first one, we can make it a homogeneous solution. So grab these 3 equations and see what happens when you put them together. Okay, so this is your new system of linear equations. I want to clarify that the bottom 2 rows, we got them because R's 1, 2, and 3 are defined. And for the first one, we made the first row equal 0 because it's going to help us perform Gauss-Jordan elimination. It's pretty hard to perform Gauss-Jordan elimination if one of the solutions happens to be a variable. So we have this. What next 2 steps are we supposed to do? And if you said to convert this system of linear equations into an augmented matrix and acquire the row echelon form of that said matrix in that order, you are correct. So I'm hoping you guys found a solution in a graphing calculator, or were able to do so after pausing the video, because if you did, you get a column of 1, you get column 1 of 1, 0, 0, column 2 of 0, 1, 0, column 3 of 0, 0, 1, and column 4 of 1, 2, 1. And we were just one more step closer to finishing this problem, and that is to identify the currents. So the first column represents I1, and therefore I1 is equal to 1 amp. Second column, we have that I2 is equal to 2 amps. And, oh, you guys can't see that, huh? And the third column, I3 is equal to 1 amp. And there you have it, folks. We were able to apply Kirchhoff's law for not just any network, but an electrical network.